Welcome to this Quintus Tech Talk. My name's Jim Shipley. I'm the Business Development Manager for Quintus Technologies, working with hot isostatic pressing. And today I'm going to be talking to Professor Anton du Plessis from South Africa, Stellenbosch University previously, and talking about the use of HIP with AM shelled components. So Anton, welcome to the Tech Talk. Could you give us a bit of an introduction?
Yes, thanks, Jim. So great being here. I'm joining you from South Africa. As Jim said, I used to be at Stellenbosch University. I still have an affiliation there. I've recently started working for Object Research Systems, which is a software company in Canada, working on image processing software for CT images and for microscopy images. I'm going to be talking today about hipping of additive manufactured metals. Additive manufacturing is where my research has been the last couple of years. And my colleague, Eric McDonald, is a collaborator of mine. He can't be here today, but he's from University of Texas at El Paso and also at Oak Ridge National Lab. So we've been working together for a couple of years. We're both editors at Additive Manufacturing Letters Journal, which is a short format journal for additive manufacturing research. So if you have some really exciting additive research, please submit your work there. But basically, we've been working together for a couple of years, and the first of the series of work that's involving hipping was published in 2020, which involved manufacturing small coupons of titanium, laser powder bed fusion, titanium 6 aluminium 4 vanadium. And this material is well known to have sometimes lack of fusion pores and sometimes keyhole pores, different defect states depending on the process parameters used. What we did is we intentionally created different defect states. So by varying different process parameters, we got different amounts and types of pores inside this material, imaged it non-destructively using CT, and then the exact same cube used in the imaging was then subjected to hipping and then imaged again to exactly quantify which pores close up and which do not close up and how well the hipping works. And the quick answer, you're welcome to read the paper, is it works really great. Only when pores are really near the surface is it a problem. And it worked so well, in fact, that it gave us this idea that we wanted to take it a step further, where we not only close up internal pores in solid material, but also just manufacture in the first place a shelled object with the process powder still in place in the laser powder bed fusion process. And this has some advantages in speed of processing and some other advantages as well. And that's where the story goes, really.
So Anton, what kind of speed improvements do you see in terms of the printing process? Are we talking five-fold, tenfold? I mean, what can be done with this?
So it's actually quite impressive. We did some calculations for bulky parts. If you're using a typical laser powder bed fusion machine, which has a 300 millimeter build platform, and you theoretically build a solid part filling the build platform, you get a factor of 15 time improvement by building only the shell. And then the idea is that hipping is used as a quality measure and improving the properties of these additive parts as a requirement in aerospace applications, for example. So reducing the time of manufacturing improves the total process time, and the manufacturing time in laser powder bed fusion process is a large factor of the cost. So that's it's a significant improvement. Of course, you won't be building solid blocks of material, so it's up to a factor of 10 for bulky parts, and that's where I guess the next steps of the research is interesting in evaluating how much time saving really in practice is possible for typical components.
So what about the shape change that happens as a result of the densification?
Yeah, this was very interesting actually in this work where we investigated different shell thicknesses, and in the process there were different amounts of or different volumes of powders left inside, and different amounts of deformation or different amounts of shrinkage. And it's quite amazing to visualize this non-destructively, to see exactly how much deformation takes place. And even with very thin wall thicknesses, that it still works quite well. This deformation can be predicted by simulation. So some of our team members who are software experts on simulating heat treatment and hipping processes, they made predictions for some coupons, which are basically cubes. So you have like a bloated cube, which is the pre-compensated geometry, which is then manufactured, and then the hipping process then shrinks as it solidifies the internal powder. The shrinkage results in the near perfect cube geometry as you wanted in the first place. So this proves the principle that you can predict and pre-compensate for this kind of shape change.
What about combining materials? I mean, have you thought about emptying the cans and putting in other materials inside?
Other people have thought of this, and we've in our team also thought about this. It's something that is can be quite exciting. Creating a can or geometry, pre-compensated geometry, and then adding some other metal powder inside and making a multi-metal composite. There's many different possibilities and many exciting possibilities for that. It's not something that we're actually doing at the moment yet, but it's something that one of those things that if you have an interest, get in touch, we can collaborate, or you can read our papers and try it yourself. I think there's a lot of potential there.
When you've done the CT scanning of these very, very small pores, I mean, what do you see in terms of morphology? Are they flat, round? What's the shape you see of the pores?
Well, in fact, we've seen mostly pores totally closing below the resolution of the CT scan. We've seen, it's a good question. I've, in most cases, seen total pore closure. I've not seen a pore partially closing under any of these projects that we've worked on. It is something that it's interesting that you mentioned that. I've been successful with beam time application at the European synchrotron. So in end of June, I'm actually taking some samples up there for really high resolution imaging of squeezed hip pores. So then I can answer your question better after that session.
Okay, sounds like another tech talk. Yeah. Okay, cool. So, I mean, the work you've done now, I mean, obviously speeding up the processing of the parts, maybe combining different powders, ensuring that you've got pore closure. I mean, what kind of mechanical properties have you seen for the titanium 6.4 example now?
Well, surprisingly well. The first paper that we wrote in 2019, I think, we compared rough surface, as-built surface condition for solid laser powder bed fusion manufactured tensile bars and shelled bars, which were then hipped subsequently to solidify them. And the tensile properties were identical. There's no difference. Both were quite good. In the most recent paper that was just published this year, we studied in a similar process, solid laser powder bed fusion material with rough surfaces compared to the rough surface hipped and shelled components. So in this case, the fatigue strength and the lifetime were reduced slightly, about 20 to 25%, or maybe 30% in some cases. But this is still surprisingly good and much better than not without hipping. Compared to the as-built state, it's still a significant improvement.
So I know for the powder near net shape industry, where people are combining several different powders into a can and then hipping it, it gives a lot of great opportunities to make tailored parts with different functionality in different areas. So I think there's a great opportunity there to do something really good. So I mean, looking forward now, I mean, what kind of collaborations are you looking for from the industry, from universities, from individuals? What are you trying to do now?
The quick answer, Jim, the more money people can send me, the better. No, I'm just joking. No, as a researcher, I'm pushing as much as I can, the possibilities for additive manufacturing, and additive is a disruptive manufacturing technology, allowing new things to be done that were not possible before in terms of complexity and lead times and amazing functionalities. I'm working in improving the structural integrity of these materials while making new things possible. So we want to do amazing things, for example, go to space, but we want to make sure we don't have any unnecessary accidents in the process. So I'm focusing my research on structural integrity and improving the structural integrity, and that's why I work with some researchers on fatigue properties, and hipping is a key to structural integrity in additive. So definitely working on this. This canning or shell hip combination process that we've been discussing improves the speed of manufacturing, and there's even some structural integrity advantages compared to traditional methods because of the fact that there's less thermal buildup. Because there's only a shell being built, you don't have so much residual stress, and you don't have the possibility for residual stress induced cracking. And these cracks are actually much more of a problem than small isolated pore spaces on the 1 micron scale level. So that's where my interest comes, and that's where I see my research going further in this direction, proving these processes and improving these processes, this hybrid processes.
So do you see there's some opportunities here for other alloy groups that are maybe more crack sensitive, like some of the nickel alloys, etc.? Do you see this as being that as a solution to the problem?
Could very well be. If you can if you have problems manufacturing solid parts because you get cracking in laser powder bed fusion, and you have a typical problems with bulky parts, if you now use this process and you're only building shells and you don't get any cracking, that's exactly the kind of application where this can be useful. So we've not actually studied that in detail yet, but that's definitely a huge possibility and great potential.
Right, so you see some opportunities here also to use some of the highest strength cycles that we've been using rather than a traditional hip cycle, which was actually developed for castings. This is for AM. We've been moving more towards some more tailored hip cycles, including heat treatment inside the hip. I guess that gives some opportunities here as well to further improve the fatigue life.
Definitely, and it's something that I think has a lot of potential because it's not anymore the big pores that are driving failure, and I think there's a lot of optimization that can take place there. I'm not a metallurgist, so we will be continuing this work with some experts on that area, but improving the thermal cycles in the hip process will definitely improve the combination or this hybrid material. The additive material has smaller grain sizes, and the hip densified powder has larger grain sizes, which needs a bit of a different approach than the standard hip cycle.
Well, I think we've covered a lot of ground here in this discussion today. I mean, is there anything more you want to talk to the audience about? I mean, we have a lot of people watching this tech talk.
No, thanks for watching. From my side, I'm very happy to have been involved in this research, and thankful for the support from Quintus for supporting this research and for making available their technology. I think there's a lot of potential for HIP for ensuring structural integrity of metal additive components for critical applications. This is where I see my research in quality assurance going forward. So if anyone is interested in further any topics in this area, please get in touch anytime on non-destructive imaging, understanding the influences of defects on mechanical properties of AM materials. Basically anything in that direction is of interest for me. And keep up the good work, and I'll definitely try to continue some of this work as because of this great potential that we see for it.
Excellent, yeah, and whilst I've got you on, I know that Eric couldn't make it today, unfortunately, but maybe you have some insight into the topics that he's currently working on and some areas that might be of interest to the audience.
Yeah, so Eric is working on some really great stuff. He's an expert on additive manufactured electronics, 3D printed electronics, but he's also, as I am, interested in pushing all forms of additive processes and materials and seeing how far we can take additive into really exciting application areas. For example, one thing we worked on together has been on additive ceramics, and we actually demonstrated by CT imaging crack healing of ceramic cubes manufactured by an additive process, and that was also published, but not something that we're discussing here today, but I just thought I'd mention that.
Yeah, well, ceramics are very interesting to us as well, of course, and you're probably aware we just recently had a webinar on HIP of ceramics, and there are some white papers out there on the Quintus Knowledge Center on our website. So, I mean, there's a lot going on around ceramics. We're heavily involved in this, and I think the additive manufacturing part of ceramics is becoming extremely interesting as well. So I think this is an area where we see great potential, not only for additive manufacturing, but for ceramics in general. So it's good that you mentioned that. So for everybody watching online today, thank you for tuning into this Quintus Tech Talk. I think there's been some really interesting discussions here. I think Anton and Eric McDonald together have been doing great work. Get in touch with us. We'll put you in touch with them if you don't have direct contact with them. And look forward to seeing you in future Tech Talks. There are many more coming. Look us up on the web. Check out our website and our Knowledge Center where you can find all of these items. And we look forward to seeing you soon. Thank you.
Thank you.